Welcome to Test 3B Review. Here are the 5 sections that this test covers, as well as the recommended practice problems that are on the assignments that go along with each of these sections. So these problems are already known to you. This test is very similar to the problems on this review, as well as all the problems that are listed here. So like all of our reviews, our video reviews, we will first go through the problems. Go ahead and pause when you need to, get them written down. Then you can go to the quick solutions and check your answers and take a look at any of the worked out solutions that you need to take a look at. Best of luck. These first 4 problems pertain to section 3.5. These next 4 problems go along with 3.6, the chain rule. The problems in yellow here go with 3.7, implicit differentiation, and problems 11 and 12 go with section 3.8, the derivatives of inverse trigonometric functions. And these last 2 problems go along with section 3.9, where we look at the derivatives of exponential and logarithmic functions. Please also know the natural log of e and the natural log of 1 for this test. Here are the worked out solutions. For number 1, we want to find dy dx for this function here. This function has 2 terms, so what we're going to do is use the sum or difference rules in order to find the derivative of each term separately. So the derivative of y is dy dx equals the derivative of 3 cosine is negative 3 sine of x, since the derivative of cosine is negative sine and that 3 out front will just stay. No need to use the chain rule because the inside function is just x, its derivative is 1. Here in the second term, we have the secant of 4x. Here we do need to use the chain rule because our inside function is 4x. It has a derivative that's not just 1, its derivative is 4. So our secant derivative is secant tangent or tangent secant, whichever way you'd like to write it. So it's going to be plus secant of 4x, right? We don't change the inside function, and then the tangent of 4x. Then we need to multiply by 4 the derivative of the inside function. So our final is negative 3 sine x, then plus, the 4 can come out front, 4 secant of 4x times the tangent of 4x. Problem number 2, again, we want to find dy dx. So the derivative of y with respect to x is dy dx. So dy dx equals, the derivative of 15 is 0. I'm going to write it here. We don't need to. Then minus, what we want to do is find the derivative of this product. It is a product, and we need to use the product rule because each one of our factors in our product, x cubed and then the sine of 2x, each have the variable x in them, which is what we're taking the derivative with respect to x. So we do need to use the product rule here. Our u value is x cubed, and our v is the sine of 2x. So u prime, using the power rule, is 3x squared, and v prime, using the chain rule, is 2 cosine of 2x. So, using our product rule to write our final answer, it's minus this whole thing in here. So we have u times v prime, so we have x cubed times 2 cosine 2x. We'll have 2x cubed cosine of 2x plus vu prime. So the sine of 2x times 3x squared. So we'll write the 3x squared first, and then the sine of 2x second. Now really, we can just leave our final answer looking like this, or we could multiply the negative through. Since that 0's there, I mean, we don't really need that 0. So I'll just erase the 0. And there we have it. Our dy dx is negative this entire quantity here. In problem number 3, we're given a function and then we want to find that function's derivative at 3 pi over 4. So we definitely need to break out our unit circle if you do not know those things by heart. First thing that we need to do is find f prime. Now, in this case, we could use the quotient rule. We could also not use the quotient rule if we wanted to rewrite. I'm going to use the quotient rule just to get practice with it since we've already gotten practice with the product rule. So it's low d high, so it's cosine x times the derivative of the high, derivative of 3 is 0, minus high times d low. The derivative of cosine is negative sine, all over cosine of x squared. Now, we could write it here. Since I'm going to plug something in, I'm actually going to write it like this instead. It's just visually simpler to plug something in and then square it. All right, cleaning this up a little bit, our numerator, the first term goes away. Since it's times 0, we have a negative times a negative, so we end up having 3 sine of x over the cosine of x squared. Then we want to plug in 3 pi over 4. 3 pi over 4 is in quadrant 2, so the sign is positive root 2 over 2. And then the cosine of 3 pi over 4 is negative root 2 over 2, and then we square it. So we got those values from our unit circle. Remember, the cosine is the x value at that angle, 3 pi over 4, and then the sine is the y value at that angle, 3 pi over 4. Now, cleaning this up a little bit, in our numerator, we'll have 3 root 2 over 2. And in our denominator, we're squaring, so it'll be positive. So when we square the square root of 2, we just end up with 2. And when we square the 2, we'll end up with 4. So what I'm going to do is multiply by 4 over 2 up here. That's what dividing by 2 over 4 means. It means multiplying by 4 over 2. Yes, I could simplify that to 2 over 1 if you wanted to. We can do that in this next step. So here we can simplify, and then essentially we're multiplying by 2 over 2. So we're really just multiplying by 1. So our final answer ends up being 3 root 2. If you multiplied through by the 2, you'd have 6 root 2 over 2, which simplifies to a 3 root 2. For number 4, we want to find the equation of a tangent line to our function y equals the tangent of x at x equals pi over 4. So once again, we'll need our unit circles unless you have this stuff memorized. So we need to find our point and the slope. So our point is pi over 4 for the x value. We need to find the y value. So to find the y value, we plug in pi over 4 to our function. Now remember, tangent is sine over cosine, or the y-coordinate divided by the x-coordinate. At pi over 4, the y-coordinate and the x-coordinate are both root 2 over 2. And whenever you divide something by itself, no matter how complex it is, you get 1. So the tangents of any of like the pi over 4 parts on our unit circle are either 1 or negative 1, just depending on if the sine and the cosine are like the same, both positive or both negative, or like opposites. So anyway, that was a little bit of a tangent there. Haha. So y is 1. So we have our coordinate point. Then we need our derivative, our slope. So the derivative of tangent of x, that's a pretty easy one, is just secant squared of x. And then we need to plug in pi over 4 to secant. Now secant is the reciprocal of cosine, so you can kind of write this like in either way. I like to just think about a reciprocal as just flipping a fraction, right? So the cosine of pi over 4 is root 2 over 2. That means that the secant is 2 over root 2. So the secant of pi over 4 is 2 over root 2, and then we're squaring it. So when we square that, we'll get 4 over 2, which is 2. Are there other ways to do that? Sure. You could have rationalized this and just gotten root 2 and then squared it, which is 2. So there's a couple different ways to go about getting what the secant of pi over 4 is and then squaring it. Okay, so we have found our coordinate point and we found our slope. So our last thing is to get point slope form. So we'll have y minus 1 equals 2 times the quantity x minus pi over 4. And then depending on how you need to like input this, you can get it just as y equals, or we can get it in like perfect slope-intercept form by distributing the 2. So we'll have 2x minus 2 pi over 4, which is pi over 2, and then plus 1. So this is our b value, like our y-intercept. We can just leave it written like that. That's totally fine. So either one of these is a perfectly acceptable way to write your equation of the tangent line. Problem number 5 is having us use the chain rule because our inside function is cosine of x and our outside function is like u to the negative third. So we can rewrite this as y equals cosine of x to the negative third. I haven't done any calculus yet. So it's a totally acceptable way to rewrite it. Again, we can do that for any trig function that's raised to a power. The only one that doesn't work is like a -1 because that means it's like the inverse cosine function. It doesn't mean raising it to the negative first. So just a little bit of weird notation there. But the -3 is fine, so we can rewrite it that way. And then we can clearly see that we have to use the power rule. So the power rule, to take the derivative. So the power rule means bringing that -3 out front, not messing with the inside function, and raising it to 1 less. So be careful there. It's not -2, it's -4. Then we have to use the chain rule because our inside function has a derivative other than 1. The inside function is the cosine of x, so taking the derivative of that, it's times negative sine of x. Cleaning this up a bit, it could be written in a few different ways. We have a negative times a negative, so we'll have 3 sine of x, and then in our denominator, it's cosine to the 4th power, which will, in the final answer, be written with the 4 there. In problem number 6, we have to find g prime and then plug in 2. So I'm going to first just rewrite g of x as -5, and then this 8x, since it's in a square root and in a denominator, it's really raised to the -1/2. So in order to find g prime, we want to first use the power rule and bring that -1/2 out in front and multiply it by the -5 to get positive 5/2. Then not mess with the inside function at all and raise it to 1 less than -1/2. So we raise to the -3/2. Then use the chain rule and multiply by the derivative of our inside function, 8x. The derivative of 8x is 8. So multiplying 5/2 times 8 is really the 2 and the 8 cancel and become a 4, so it's 5 times 4, which ends up being a 20 out in front. Then we have 8x to the -3/2, so that really means 8x to the positive 3/2 in the denominator. Or you can write this as 20 over, and then since it's 3/2, the 2 is our index, telling us what kind of root we're taking, to square root of 8x, and then whatever that ends up being is cubed. So we can write that either way. That's our g prime function. Now the reason I like writing it with the actual root rather than the exponential, the fractional exponent, is because when we want to plug in 2, it's easier, I think, just for me at least, to plug in when we actually have a square root. So g of 2, I'm going to plug it in to this function here. They're the same again, but this one's easier, I think, to plug in a 2. When we plug in a 2, we'll have 20 over, and then 8 times 2 is 16. So it's a square root of 16, and then that's cubed. So we'll have 20 over, the square root of 16 is 4, so it's 4 cubed. Again, you could do 16 cubed first and then take the square root, but I don't know what that is, so it's easier to do this mentally first. So 4 cubed is 64, so we have 20 over 64. That can be simplified because both of those are divisible by, divisible by 4. So 20 divided by 4 is 5, and 64 divided by 4 is, doing this in real time, guys, I'm struggling with mental math right now. Oh, help me. is 16, duh. Okay, so our answer is 5 over 16. In number 7, we have a pretty complex inside function and actually another inside function inside that inside function. This is like the Russian nesting dolls problem. So we have our outer function is something to the third. So in order to find dy dx, we use the power rule. So we bring that 3 out front. We don't mess with the inside function at all. And we raise it to 1 below 3. Awesome. So now we take a look at the inside function. This giant inside function has a derivative that we need to multiply by. So the derivative of that inside function, the derivative of 1 is 0, and the derivative of cosine of 2x is negative sine of 2x. And then we have to multiply by the even more inside function of 2x, which is times 2. Its derivative is 2. So that one was a double chain rule problem. Cleaning up, on the outside, we have the 3 times the 2, and we also have this negative 1. So on the outside, we'll have a negative 6. And then we can write these in either order. I'm going to put the sine of 2x first. And then we're multiplying by 1 plus the cosine of 2x, and then that's squared. So really, as long as the negative 6 is out front, the order of this term and this term, or this factor rather and this factor, does not matter. Here we want to find the equation of the line tangent to the curve, and this curve is defined with the parametric equation where the x-coordinate and the y-coordinate are both defined in terms of a third variable t. And so in order to find dy dx, we need to find dy dt and divide it by dx dt. So finding dy dt, the derivative of y with respect to t, that derivative is negative 2 sine of t. Then dx dt is the derivative of x with respect to t, which is 2 cosine of t. Sine over cosine is tangent, so this is negative tangent of t. You could have left it just like this, totally fine. We would get the same answer in the end. So in order to find the derivative, dy dx, when t is pi over 3, we have to plug it in here. So we're looking for our derivative, dy dx, when t is pi over 3. So we need to find negative the tangent of pi over 3. So in order to find the tangent, we do the sine over the cosine. So the sine of pi over 3 is root 3 over 2, and then it's negative. So it's negative root 3 over 2 over the cosine of pi over 3, which is 1/2. Here, when we have a complex fraction, both of our denominators are the same, so they can cancel. So we have negative root 3 over 1, so our slope is negative root 3. That's our slope. The instantaneous slope of the curve at t equals pi over 3. The next thing we need to find is the coordinate point. So our point has both an x and a y. So in order to find the x-coordinate and the y-coordinate, we need to plug in to our x and our y at pi over 3. So our x-coordinate is 2 times the sine of pi over 3, while our y-coordinate is 2 times the cosine of pi over 3. So the sine of pi over 3 is root 3 over 2. Where the cosine of pi over 3 is 1/2. This value is root 3, and then this value is 1. So our coordinate point is root 3, comma 1. So now we have a point and a slope. Then we need to go into point-slope form. Point-slope form is y minus 1 equals our slope x minus root 3. If we wanted to write this in slope-intercept form, we can distribute the negative root 3 through, and then when we multiply negative root 3 times negative root 3, it actually ends up being 3. Then when we add 1 to both sides, we end up with negative root 3 times x plus 4. For problem 9, we have a function that is defined implicitly, so it's not y equals. So what we need to do is find dy dx. So in our first term, we have a product. So our u is x cubed and our v is y. U prime is 3x squared, where v is 1 dy dx, since we're taking the derivative with respect to x. So in this first term, we have u times v prime, which is x cubed times dy dx, plus v times u prime, which is 3x squared times y. Then we need to take the derivative of the next term with respect to x, so it's minus 2 times dy dx equals the derivative of 5 with respect to x, which is 0 because 5 is a constant. We want to solve for dy dx, so we're going to subtract the 3x squared y from both sides since it doesn't have a dy dx in it. So we're left with x cubed times dy dx minus 2 times dy dx equals negative 3 x squared y. To get dy dx by itself, we factor out the dy dx, and we're left with x cubed minus 2 equals negative 3 x squared y. We can then divide both sides by x cubed minus 2 in order to get dy dx by itself. So we end up getting dy dx, the derivative of y with respect to x of our implicitly defined function, is negative 3 x squared y over x cubed minus 2. In problem 10, we again want to find dy dx of this implicitly defined function. So to find the derivative with respect to x of each term, the derivative of x with respect to x is 1 equals the derivative of 3 tangent y with respect to x is 3 secant squared of y times the derivative of y, our inside function using the chain rule, is dy dx. So we want to solve for dy dx, so we need to divide both sides by 3 secant squared of y. When we do this, we'll be left with dy dx equals the reciprocal, basically, so we have a 1/3. And then we have 1/3, and then the reciprocal of secant squared. So the reciprocal of secant squared is cosine squared of y. Problem 11 is finding the derivative of the inverse sine of 4x squared. So our derivative rule for sine, inverse sine of u, to take the derivative, it's u prime over the square root of 1 minus u squared. So let's identify what u is. In this case, u is our inside function 4x squared, and u prime is its derivative, which would be 8x using the power rule. So finding the derivative of sine inverse of 4x squared using our formula, our formula for it, is u prime, so 8x in the numerator, over the square root of 1 minus u squared. Simplifying this, we'll have 8x up top. Squaring 4x squared gives us 16x to the 4th. For problem 12, we want to find the derivative of the inverse tangent of negative 1x. So using our rule for the derivative of the inverse tangent of u, our inside function being negative 1x, it's u prime over 1 plus u squared. So if we identify what u is what we're taking the inverse tangent of. It's negative 1x. So u prime is negative 1. Using our formula for the derivative of inverse tangent, we'll have negative 1 in the numerator over 1 plus u, negative x, squared. When we square negative 1, we get 1, and when we square x, we get x squared. So this simplifies out to negative 1 over 1 plus x squared. For problem 13, we need to remember that the rule of finding the derivative of e to the x is just e to the x. Then if we need to use the chain rule, we'll multiply by the derivative of the function that's up in the exponent. So remember, in order to find the derivative of e to the f of x, we take the derivative of what's up there, f prime of x, times e to the f of x. So that's using the chain rule. We could have also written that as e to the u. Either way is completely fine. So when we take the derivative of each term here, so in our first term, e to the 3x, we take the derivative of what's up top, so 3x, the derivative's 3, and then multiply by itself, e to the 3x. Boom, we're done with the derivative of the first term. The derivative of the next term, here, we do the exact same thing, except we already have a 3 out front. So we have that 3 out front, then we multiply by that 3 up top, and then do e to the 3x. Then our last term is a product. So we need to use the product rule. Our u is x, and our v is e to the 3x. U prime is 1, and v prime is 3e to the 3x. So when we use the product rule, we'll have u times v prime plus v times u prime. I don't really need those parentheses because I'm just adding it anyway, not subtracting or distributing anything through. So cleaning up, what I'm going to do is actually factor this entire equation. And in every single term, the only thing that we have in common is an e to the 3x. So what we're left with from our first term is a 3. What we're left with our second term is a 9. What we're left with in our third term is a 3x. And what we're left with in our fourth term is just a 1. When we clean that up even more, we have an e to the 3x out front. Then we're left with 3 plus 9 plus 1, which is plus 13. And we're also left with a 3x. The reason it worked out that way is because these could have initially just been combined as one single term for e to the 3x. I just wanted you to get practice with doing the derivatives for a bunch of e to the x's. Our last problem is again having us find the derivative. So the rule for finding the derivative of ln of u is u prime over u. So it's 1 over u times the derivative of u, so u prime over u. So that's our rule. So finding the derivative of this, our u value in this case is 5x, so then u prime is 5. So if we find the derivative, u prime over u, we end up with 1 over x, and it is that simple. Now on to the quick solutions. For number 4, note that you can write that either way, so long as you solve the equation of the tangent line for y. Note that in problem number 8, I did get the equation of that tangent line in slope-intercept form. For problem 13, I factored and combined some like terms. I hope that review went well for you. If you have any other issues, make sure to join my office hours when you can. And most of all, have fun on your test. Bye-bye.